Hey, this is Nate here, and what you see here is just this basic platformer I have set up in GameMaker. And in this video, I'm going to go over the collision system that's being used here, and also how to set up the other parts. This platformer has slopes, and it has one-way platforms, also double jumping and wall jumping, plus the movement has a slight acceleration and deceleration to it. So, a lot of the basic stuff you'd see in most platform games. One thing unique about the collisions is I don't use any kind of while loops. Everything's done just with the bounding box of an object, which resolves the collision. And that includes these slope tiles are not precise tiles at all. They're actually just a little bit of math that makes it lerp up and down the slope. That'll be the second part of the video, showing how to do the different types of collisions. The first part's going to focus just on how a basic rectangle collision works. So, and everything kind of builds off of that. And because of that, though, everything's really fast. So I can spawn like 100 objects and there's no problem. It still runs really fast. In fact, if I keep spawning, it does 100 at a time when I hit this button. It takes about 5,000, there we go, 5,000 player objects to actually drop the FPS below 100, which is not bad. Nobody needs 5,000 player objects, but if you do it, this would do it, no problem. So that said, here's some code I posted on Pastebin a while back, which is the math behind this the collision system that I shown there. And when I have like just a small solution, I like to just throw it on Pastebin because it's easy to share out. And this solution, it uses a lot of the built-in movement and stuff, and this is how to set up the create and the step event. And that's really not the focus here. That's just there for like, here's a basic platformer. And then at the bottom here, I have the collision event, which shows how to do the math that would use the bounding box of an object to resolve the collision. And that's all it is. So it's not, there are disadvantages to using a collision event and the built-in movement. But if you're starting out, this is like something to learn off, something simple to set up. And what happened when I posted this too was, I guess it ended up in other tutorial videos, this math. However, instead of just using it correctly, people stuck it in a while loop. And the problem with that, right away, as soon as I hear, oh, they're doing this math in a while loop, I know there's going to be floating point errors that come up, which is going to cause your while loop to freeze or infinitely lock up the program, because there's those floating point errors might make it so that the math here doesn't actually resolve the collision, and the collision's going to keep firing over and over and over. So and I believe people have used like kind of band-aid fixes of adding like a small value to it and whatnot, and that works, but there are some problems with that too. And I can show here's one of those other implementations. This isn't mine, that it uses my math, but then it does that band-aid fix I was talking about. But as you can see, it still jitters if you zoom in, and the reason for that is I'm using small values of movement, and those are smaller, and then what's happening, those floating point numbers are conflicting with the small acceleration and deceleration. So if you're moving in whole pixel values, it might not be a problem, but or maybe just larger values, but if you're moving in very small amounts, it will. So when you have acceleration and deceleration, you're going to see how the wall, if I zoom in, you can see it jitters. So not ideal, but for some cases it might work. Now for the purpose of this video, I'm going to gloss over a lot of things. This isn't necessarily like an advanced tutorial, but we don't have time to just stop for every little function and thing. And I highly encourage people to always use the manual, because if you see a function that I use and I don't really explain that function itself, you can always open up GameMaker and the manual and check it out. So like if I look at just any function, if I middle mouse click the function, it brings up the manual right away, instantly. It even gives you a little code snippet on how to use it. Where's a better one? Here's as you can see, instance place list, and ta-da, we have like a whole code snippet of how to use that function. So I highly encourage, if I gloss over any kind of terms or whatnot, to crack open the manual and check it out. You can, and also if you want F1, does the same thing. F1 or middle mouse. Very useful feature of GameMaker. And on that note too, GameMaker, one of the big advantages is the manual. If you've used stuff like Unreal and Unity, they are definitely more advanced and they have more features, but their manuals are not user friendly. GameMakers are. There's parts in that manual that teach. So I think every tutorial should actually maybe take a second, like I just did, to say, hey, use the manual. If I skip something, use the manual. It's usually explained. You'll learn a ton from it. So anyway, with that said, I'm going to explain the math on how those collisions work first, and then a basic code implementation for it. All right, so let's just say this box on the left is the player, and then this one on the right is some kind of wall or collision object. And if the player is moving to the right, eventually, they're going to come over and they'll be overlapped by some amount depending on how fast they're moving. And just imagine it's there. And in order to resolve that, then the player object would, of course, go to the left by some amount and put it flush with this wall, or the left of this wall. So on the left here, I'll just draw kind of a yellow line down here. Every instance has a bounding box or collision mask. And on the left side, it's going to be, in GameMaker, we'll have the B box left. And so B box left minus something, we can call that whatever, n minus n is going to put that object flush. And what n is, if we look at this player object, let's imagine, just for simplicity, the origin is in the center. N is going to be this little amount right here. Okay, now we don't want to just take the width and divide it by 2, because what if the origin's here? It might be kind of weird to put the origin there, but it's good to account for stuff like that. So n could be this also. In any case, we have basic properties of this object that we can find that regardless of where the origin is. So what we can do on this right side of the object, the player, sorry, is the B box right. And to find this n value, it quite doesn't matter where the player object currently is, because the B box right relative to the origin, let's put the origin back here, and it's got an x and a y, of course. B box right minus x is going to be n. Okay, it's gonna give you this right here, because you got this B box side minus x, and that'll give you n. So of this wall, B box n or B box left minus n is where you're going to want to place the x value. So let's say it was right here, and then you're going to have it'll now be flush. So and the same's going to work if you're moving this way and this way and this way. And one caveat is you have to be actually moving, like have a movement value for your x and y, like a velocity or something that's not 0. If you're moving 0, we're not going to know whether to do the math to resolve it with the B box left or over here, because the math's not going to be identical here. We're going to use B box right, and we're going to find a different n value. We're going to find this right here. So it's going to matter whether we're moving left, right, up, or down. So, but that stuff's easy to do. We have speed values. If you saw when on the paste bin, what I used was just the x previous and y previous with the current x and y, and then I was able to find where they moved from there. But for the implementation I'm going to show, we're just going to use the actual movement values of the instance itself. So now the next part, however, this is just collision with one wall or one collision object. To do multiple, we're going to have to do something a little different, but this is the basic math, and it's just repeated, and I'll show you how that works. Okay, so what I drew here is, let's just imagine all these are wall objects placed arbitrarily. It's probably not a great way to place them in your game, but it illustrates how we can do multiple collisions at the same time. So going back to the B box left, all these objects have a B box left, right? And what we want to find is what is the minimum of that n value, or whatever distance we wanted to call it, that little value here. What is the minimum that we end up with after we subtract it from all the bbox lefts here? So this is why you don't have to use a while loop. You can just simply use one instance place list, and you'll get all these objects at the same time. So let's imagine this object's moving fairly fast, or maybe this is just zoomed in, and it goes all the way to here, and that means it's in contact with this one, maybe a little with this one, this one, this one, and this one. I guess we didn't hit that one. So it's in contact with all of these. So what we do first is, while it's in contact, right, the origin is now here. Sorry, it's hard to see. Origin. And it has an X and it has a Y. So we're going to set some value. We'll just call it Rx for resolved X. It's going to equal the current X. And then we're just going to take the minimum using the same math as before. The minimum that we of whatever happens when we do each of them. So it's going to be, you're going to set it to the X, and then we're going to just loop through and have Rx equals min Rx, and then right here I'm just scribble in, that's going to be repeat the math for each object. And that's why, you don't have to use a while loop. You can just find the minimum and boom, there you go. And then those floating point errors are no longer a problem. And you only have to use a single collision function. So, and it works the same way going left, right, up, down. Just find the min or the max. So if we're going, from the player's over here and we're moving to the left, instead of finding the min, we need the max, because on the x-axis, this way is positive and this way is negative, right? So we find either the min or max resolved position. And then what's nice too is everything's just basic arithmetic. Arithmetic is extremely fast. We don't have to do anything too complicated. So next I'll take it over and show how that looks in code. All right, so right here, I have this basic player object, and it doesn't have a create or doesn't have anything assigned or whatnot. It's just basic. Here's a player object just to show. This isn't going to be the platformer object that does like the slopes and whatnot, but this is just to show how the math works first. So in the step event, I've just set up just a basic, your X and Y input accesses, and I have a DS list. That's where we're going to store the collisions, and then a velocity. We're going to start them at 0. Normally in your create event, you're going to set up some movement values and have an actual instance variable that goes with the object. But just to show the basics, so that there's no other clutter, we're just going to do everything completely local and not deal with any of that. So, and if either of those axes are pressed, we're going to move. We're going to just do some simple trig to move, and I hard coded a 6 whatever for movement. So after this happens, this is basic movement. Velocity is either still going to be 0 or it's going to have some kind of value depending on the direction. And so here, to do the horizontal collisions, the first thing we're going to do, we're just going to move on the x-axis by whatever the amount was, right? And then right here, we're going to use instance place list, which it's going to populate this list we made up here with whatever collisions have occurred, and we have this generic abstract collider object. A lot of people use like walls or something like that. They don't need to be sorted, and you supply the list. And again, use the manual if you haven't used functions like this. Now, instance place list is definitely more costly than some of the other collision functions, but we only have to call it once. So kind of depending on how your game's set up or how many collisions might happen at once, this ends up being cheaper because we're only calling it a single time, and then we're just iterating through it and doing some basic arithmetic. So, and what it returns is the number of collisions. So if there have been collisions, I'm gonna first remember I called it Rx in the example, but it's I'm gonna I like to spell out my variables so we know exactly what's happening. So Rx, we started at X, we've already moved. And then we're going to check if velocity is greater than 0, meaning we're moving to the right, or if velocity is less than 0, that means we're moving to the left. If velocity is 0, that means we didn't even move, and this probably wouldn't have triggered anyway because this list wouldn't have been populated. But and then at the end, we're going to set x to whatever that minimum or maximum value that we found was. So it's just a simple for loop, and then it's going to, here's the min. It's going to, exactly like I showed when I drew it out, the resolved x, and then it's going to go into that list, b box left, and then this is that how you find that n value I was talking about. And then that's for moving to the right. Then moving to the left, it does the same thing, but we're going to do the max because we're pushing the object to the right. We're moving right away from where we went. And then there's just a simple x minus b box left. Again, it gives you the n value. And that's all there is for the horizontal collisions. So it's quite simple. It doesn't have any problem with the floating point, which is nice. And it also, right here, I do add ahead by 1 pixel. So for moving right or left, we take the sign of it. And that accounts for just any kind of weird GameMaker type problems with the B-box. Because if the B-box, or the B-box, bounding box, if it has any kind of discrepancies, this will cover it by a single pixel. When you push up against a wall and you have some kind of a really, really small acceleration, you might see that jitter also, but this takes care of that. That way we're not worried about having less than 1 pixel movement. So it handles sub-pixels basically. I guess that's a shorter way to say it. But and the same thing here in vertical, I do that 1 sub-pixel thing. And this is pretty much identical to the horizontal. And again, this part, I do clear the list. Right here, the list should already be cleared because it was created at the top. But you clear the list, you populate it again, and this time you iterate through checking if we're moving up or down, and we find the min or max, and it's the same way of finding that little n value and resolving it. So if I run this, I have this placed in there, and the camera's following it. Again, this isn't the platformer part. As you can see, it works pretty good. I can go down here. It doesn't have slopes or anything. It's just doing regular rectangle collisions. We can zoom in. I placed a whole bunch of arbitrary things just to see how it works. Kind of moving fast, but and there you go. That's how the basic implementation would work, minus these other fancy features. So next part, I'm going to show how to add the other parts. And it all builds off this math right here. So for this last part, I'm going to show the actual project here. That's the platformer template, and it'll be available for download in the description. And there's a lot of code there it would take too long to go through line by line, but I'm going to go over like just the general design and how it's set up. So it has an initialization room that it loads first, where a GameInit object loads kind of the main parts of the project, and it goes through it has an init step, and it goes through and it sets up the window and the resolution, and it creates the camera and the game state, and then finally at the bottom it just goes to whatever the load room is, which you can set here in the variables tab. And throughout the project I have little to-do things that are just kind of like hints on like a good spot to add to the project, or where you would add different features or whatnot. So and then it does create the game state and the camera, and the camera is just your generic camera, follows a object and stuff, so I'm not going to go over that one. But the game state is an important object here, and it acts as the control of everything basically. And as the room, when you change rooms and stuff, it goes into a state that doesn't execute anything anymore. And the main reason for having a game state like this is the player objects, entities, whatever, they don't actually use a step event. Instead, it's executed from the game state itself, and it's called event tick that way. And if you look, not room load, gameplay, you can see it does with entity event tick. An event tick's just a variable that's bound to a function for that object. And when I get to the entity, you'll see how that works. And then it passes in a tick rate. And the tick rate is just it's a delta time implementation. So here in the create, you can see It uses this, I just call it frame speed, and if the game frame rate is not fluctuating, it'll return 1. If it's going up or down, it's going to return either like 1 point something or 0.9 something, or it depends on, you know, how much it fluctuated. So, and then whatever the room speed is, so you don't have to be like 60 frames per second, and it'll return 1, and that way it passes that to the event tick, and then all your timing and movement stuff, if you need to keep it constant with the frame rate, you can just multiply it by that, because if it's 1, which is constant, multiplying by 1 is not going to do anything. So, and it handles game pausing here. I don't use a global for the pausing. The game state handles that. There's some generic pause, unpause functions. Again, these are just have to-dos to, hey, here's how you might want to implement things, you know. And of course, this is just one implementation. You could gut out all this, remove it, and just use like the platformer and use an actual step event. So, and all the other events are just generic. It's kind of sets up each step what's required for there. So, now the main part is how the classes work, and the inheritance is set up for the player itself. So the entity class is kind of the root of everything. And I use class, object. You know, GameMaker's it's not truly object oriented, which isn't a big deal, because games actually, composition is better in games than inheritance anyway. But when I say class, I mean object, of course, and it's inheriting from it. So the core thing with the entity is it's responsible for having collision or being in the world. And let me get rid of this inspector. I don't like the new inspector. It's just clutter. So the event tick variable here points to the function entity event tick, and then move collide state points to entity move collide state or function. And those are meant to be, you know, swapped out by something that would inherit from it. Because if we go to the entity library, you can see event tick just returns true. It doesn't do anything. And then entity move collide is very much similar to that basic player setup. Let me open that just to compare. As you can see, this is where it shows how it resolves the collisions on the horizontal and vertical axis. If we go back to the entity library, it does the exact same thing, except it does set that on vertical and on horizontal. These are basically whether it's touching the wall, the ceiling, left or right, etc. So if you have like an on ground variable, well, on vertical would be that when it's positive, meaning it's pointing down. And then the math here is that the math is actually not here. What it does is it calls a collide function from the collider. And when I get to the colliders, I'll explain how that works. So instead of, if you look at the basic player, it's doing the math here for that min max to find the collision value, or where the resolved x and y is. Here it's just sending it off to this function with its ID, and then that math is happening over in the collider, and then it's being returned. So, and that allows us to use different colliders without having to, you know, the object itself, the entity, doesn't care what it's colliding with. It just knows to call this generic or abstract collision function. So again, the math doesn't happen here, it happens elsewhere, and you'll see when I get to the colliders. And then I do vertical first, because there's a few advantages on how I do one-way platforms is kind of clever, and it works better to do this one first that way. Let's see. So that's the entity class. Again, it exists in the world, and it has collision, and it can move, but it doesn't actually move itself. It's just there for something else to control it, like a controller type object or input from a player, and that way, if your entity, it would be inherited by like a character, like a player character or an enemy character, you could have something else controlling it, and then the collision will be, you know, bound to that object. So, and I didn't show the create event. So the create event, when I say bound, I mean I'm using method, and I'm passing in the instance ID along with whatever that variable was pointing to. It's pointing, in this case, it's pointing to a function. It's just like a function pointer or reference, and it binds it, saves having to create another variable, so just binds it to there. That way, when the game state calls the with function, or the with statement, right here, that way when it's calling that, if you don't bind it and you set it up this way, the scope won't be correct. But this way, you know, it's actually bound, and the scope will be correct and execute on this instance itself. So, and collision list is the same as before, except this time it's an instance variable because there's no reason to create it multiple times. So, and then the platformer class or object inherits from entity. You can see it's the parent, and it actually does movement. So as you can see, the event tick, it overrides the event tick with a different function, and I'll get to what function that is. Platformer event tick, and there's platformer locomotion. And this active state is specific to this platformer object. If you had an enemy, you might have a different type, like an enemy AI state, and you would swap those out, so it's meant to, like, again, it's a composition, so we're able to swap parts out as we create new objects, and that reduces redundant code, and it makes it a lot easier to add new things and new ways of, new features without having to recreate certain things, because they're all handled in a very decoupled manner. So, and then it has all these movement variables that you can set: move speed, whatnot, acceleration. Anything on a variable tab like this is meant to be changed by whatever inherits it. And if you look in the create event, velocity XY, jump remember, jump count, there'd be no point in changing these, because these are set as things change. The velocity in X and Y is set by the inputs, so there's no reason to put those on the variables and clutter that up. It's stuff here on the variables definition are stuff you would, as a designer, you would change, and here these are just the instance needs these to function. So, and again, it binds the active state, which is pointing to platformer locomotion. So if I go to the platformer library, I'll show what those are. So the event tick, if you just think of this is a step event basically, except instead of putting it in the step event, we're putting it in a function, and we're binding that to the object and calling it with the game state. And that allows us to pause the game. We can pass this tick value, which is delta time. We can speed up the game by maybe multiplying that by a factor or something, the tick rate by a factor. It's kind of useful. So this is basically just a step event. And it calls the active state, which was, in this case, it's pointing to platformer locomotion, the function below it, which is bound to the object. And then move collide state is calling back to where it inherits from entity to actually do the movement and then resolve the collisions. And also another note, if I go back to entity collide, you'll notice velocity X and Y on the entity part, it doesn't actually use those as instance variables, so it's very decoupled. So it doesn't care how the thing is moving, it just needs to know these values. So these values are actual instance variables when we look at the player or the platformer object, and then they're altered through this platformer state below. So in platformer locomotion, I'm not going to go over every line, but it has your inputs, jump remember, which is just a gameplay thing. It feels nicer to buffer the jump button, and then the two main states. So this is a state machine. It's not a finite state machine. I don't use finite state machines because they're very clutterful, and you end up having tons of redundant code. So if I do have many states in a game, I would use concurrent states, which are much nicer. But if there's a low amount of states, just some logical branches work a lot better. So right here I got on vertical, which is the same as on ground. So when you're on the ground, this is basically the on ground state, this section right here. And then else, meaning we're not on the ground, so we're airborne, the airborne state. And then at the bottom, it has acceleration and deceleration. And those are at the bottom because this X speed value could change depending on which state you're in. Because when you're in the air, it's multiplied by an air control value. That way, your air control left and right is not as fast as when you're on the ground. It just feels better from a gameplay perspective. And on the ground, you have where right here, down and jump held. That's where you drop down through a one-way platform. And then, of course, your normal jump happens. And here you have your on horizontal, which is not on a wall. So you have in the air, you have two states. You could be either touching a wall or just in the air, free floating. So, and that's where you have your double jumps. And up here's gravity. And on the wall, you can have, there's a wall jump. And if not, you just slide down the wall slower. So there's some, as you can see, on wall friction. You slide down the wall a little bit slower. And then I use a jump angle. The way I do wall jump is you take 90, which points up, and then you either add or subtract a specific angle from it, and then you just use the trig functions to point your jump, your X and Y velocities in that direction. So real simple. And when I get to the colliders, I'll explain how one-way platforms work, but I don't use any specific state. I don't even use extra variables to do it. There's a little clever way to do it, basically by using Y previous and Y, and you add a value to them. And then in the collision, the collider itself, there's a way to catch that and not have to really do anything else. And you'll be able to drop through a platform just by dropping down 2 pixels and doing that. So, and when I get to the colliders, I'll show that. And the last part is the actual platformer player, like the actual reified object. All these events here are just for like demonstration purposes. You could actually delete them, and everything that it inherits is enough for this to function as an actual player. These are just here, so escape, game end, backspace, game restart. These are again just for demonstrating and playing around stuff, and then it draws some GUI stuff. So that's it for the actual entity inheritance. And if we look at the colliders now, the base collider is basically, just your box shape, and it uses the same thing where we're doing a composition. We're using different variables that point at different functions, and then in the create event, those are bound again with that instance in mind, passing its ID. So that way, back where the entity calls it, the entity just calls collide right, left, top, bottom, and these are actually pointing to an actual function somewhere in the collider library, which is right here. And let me close those. Okay, and then before I get to those, you can see here's the one-way platform. It just has collide none and then a special collide bottom, because one-way platforms only really do anything when you're going downward and touching them, and where you would either drop through or it would do a regular collision and keep you from falling. So same with the slope. It looks just like the solid, except it has a slope version of the same functions, which do a little different. So, and these slopes are not precise masks. They don't need to be. For just a basic up and down slope, it does a lerp, and I'll show how that works in a second. So, and if you look at the solid box shaped ones, this is the same math I used on the basic movement but previously, and you can see this is just doing the same math, and it's returning it as a function. That way it's all abstracted out. If we're hitting a solid box, it's going to return your basic collision resolution, and there's really nothing different here than the previous math. It's stuck in a function somewhere, and then it's bound to the object. And a collision none if you do need a case like the one-way platform where it doesn't do anything. So the one-way platform, this is it. This is all you need to do a one-way platform. And if I go back, I'll just show where platformer library, back where you drop through, it adds this constant is 2, so it adds 2 to the y and adds 2 to the y previous, and then it also ensures that the velocity is at least positive. That way your collisions will catch it that it went down. So just in case, that's sort of if you were to, let me zoom in, if you were to drop down right here, you wouldn't want to drop down because you're also hitting a solid. But in order to hit that solid, you need your velocity to be positive going down. So it just adds like a tad bit to it. So if you drop down here, basically it'll do nothing. If you drop down here, it'll drop down like that. So so yeah, you just add to the y, and then make sure you add to the y previous. And that'll really cause no problems with other code that relies on y previous, because we're doing them at the same time. And over here, what it does is it takes the y previous that we moved down. So if this is false, we drop through the platform. If this is true, it's going to do the regular bbox top collision resolution and return that. And what's nice about that is there's no extra variables. This will work on any object. These are all, as you can see, they're all, I'm colorblind, but I believe they're yellow, built-in variables, and it's really simple. So, but if we do add 2 to the, a small value like 2 to the x and y, it's going to cause this to be false, because it'll basically trick it into thinking that the bottom of the thing, or the bottom of the object, the bbox bottom, did not pass through it. It's like it's already through, or it didn't pass through in a single step. So it's just a clever way of tricking it without having to keep a whole bunch of states. Like I've seen like a fall through state or whatnot, and or even I've seen collision masks where people delete the collision mask or remove it, and then they drop through and they put it back. You don't have to do any of that kind of stuff. All you have to do is just do some simple comparisons. You can see it's arithmetic, and it's a really cool way to do one-way platforms. So, and then the slopes, I'm not going to go over all these. Essentially what it does, it's easier to see visually, of course, is it takes, if you look at the bottom left corner of this player, it just compares where that bottom left is between the left and right of this triangle. Let me move these if we focus right at it. So wherever this bottom left corner is, it takes that position, and then it takes it as a position between 0 and 1, and it lerps that position between the B box top and B box bottom of this collider. And it depending on if the collider is mirrored or not, it'll invert it. That way, if you mirror it this way or this way, it'll work. Of course, if you go this way, it's going to look at the bottom right corner instead of the bottom left. And that's all it does. It just lerps it up and down. It's very simple. I can run it and just show. Hold on. Switch video. Okay. So you can see it's just lerping up and down. That's all it's doing. It still acts as a precise collision mask, and then of course when you're not there, it just acts like a normal solid whatever. So this one's really steep, but that's all it is. It's a slope just done by lerping up and down. It's really great solution. There is one slight disadvantage I can show, and it's kind of a compromise for having like a really fast way of doing it. If I put a collider above it, because it's actually forcing the Y value to go up, you'll see it kind of clips into there. So that could be, you could add extra code to check for that, or just design your levels to be to not have that. So, or of course the other option is use actual precise collision masks, which this project you could definitely do that just by adding different ones here, different types of colliders, and use precise masks and add some different math there. But usually when you start doing really precise collisions and different options and angular type, the way the objects hit each other, it's better to just use the built-in physics and not have to code it from scratch. It's a good learning tool, of course, if you want to learn how to do it, but the built-in physics will do that, and Box 2D is very popular. Some people worry that their game's going to feel like a physics simulator or something if they use Box 2D, or it'll be like Little Big Planet. That's completely false. You have to set it up correct. That's the big caveat. If you use the default settings for the built-in physics, yeah, it'll feel kind of physics sim and floaty and jumping. But there's a lot of variables that you can configure, like linear damping, and add different forces when the player's in the air, and it'll feel just like a normal platformer, and it won't feel like a physics sim at all. And it'll take care of all those different really complex collision stuff. And that's why this project stops at these simple slopes. Because once you start to get an advanced one, there's really no point when GameMaker already does that stuff for you. It's definitely, I encourage people to use the built-in physics when they need them and not worry about it being like a physics sim or whatnot. So anyway, that's the whole project and how it works. The project will be in the download link in the description, and hopefully it helps you in your own projects. And this is just one implementation of it, what I would call more of like how that math was intended to be used, because I've seen it used in different ways that don't really work. So anyway, thanks for watching.